can start. Would you like to put in full screen, Tuncay?
Yes.
Good. So the second speaker of the session is Professor Tuncay Aktosun from University of Texas at Arlington, and he will talk about Soliton solutions to a system of nonlinear evolution equations associated with a third-order ordinary linear differential equation. So please, Tuncay.
Thank you, Ricardo. So we're in the middle of our conference, and so it has been very beneficial to attend all the colleagues' talks so far. This is joint work with my former PhD student, Mehmet Ünlü, and current PhD student, Ivan Toledo. In fact, Ivan will be graduating this August, and also my colleague from Morelia, Mexico, Abdon Choken. And this is related to the inverse problem for the third order linear differential operator. Oh, sorry. So it's so here's the outline of my talk. So even though all the experts are familiar with the inverse scattering transform method, I will just remind the audience what the inverse scattering transform method is and mention about integrable system of nonlinear equations, and in this particular case, a pair of integrable nonlinear system. And the special cases of those will be the Savada-Quatera equation, and the Kav-Kupperschmidt equation, and the bad Boussinesq equation. Actually, the good Boussinesq equation is also a special case of this. And then I will mention the direct and inverse scattering for the third order equation. And I will mention how we approach this problem slightly differently from others. And then I will mention the Riemann-Hilbert formulation of the inverse scattering problem, and I will omit the Marchenko formalism because my goal is to basically the application on the integrable systems for this talk. And I will mention the relevant prior work, and then mention the reflectionless case where you obtain explicit solutions, so-called Soliton solutions or Soliton-like solutions. And if I have the time left, I will just do a Mathematica demonstration where you put the input for input data into Mathematica, and then Mathematica will spit out the appropriate potentials and do the animation. So here's the inverse scattering transform method. So you are interested in the initial value problem for a nonlinear PDE. So you're given the initial value, u of x0 at t equals 0. You're given either you can call this the initial potential or the initial profile, and you would like to solve the nonlinear PDE and get the time evolution of that initial profile. Well, in case this nonlinear PDE is integrable in the sense of the inverse scattering transform, instead of solving this directly, so you can solve it in 3 steps. So you interpret the initial profile, the initial value of the nonlinear PDE as the potential at t equals 0 for a linear equation, and this appears as a coefficient in that linear ordinary differential equation, and at t equals 0. So you solve the direct problem for that linear ordinary differential equation, and from the potential, you get the scattering data at t equals 0. And then you time evolve the scattering data from t equals 0 to some t, and that time evolution is somehow determined by the time evolution here. But it is rather simple because you've divided something complicated into 3 steps. The first step, the second step, and the next step. And since you do this at fixed t, but rather arbitrary fixed t, now you do the inverse scattering for the linear problem, and from the scattering data you get the potential, but you do this at time t, and when you do that, you get the potential at time t. And well, it's so nice that that potential at time t happens to be the solution to your nonlinear partial differential equation, and at t equals 0, it reduces to the initial profile. So this is how you solve the initial value problem for an integrable nonlinear PDE. And basically, to get the linear ODE associated with the nonlinear PDE, or vice versa, so you use the lax pair, and so this is the ordinary differential equation, and this is the spectral parameter, and the potential appears as a coefficient in the linear differential operator, and A, the linear operator A, determines the time evolution, but it's still a linear ordinary differential operator. And the rules are that there are 3 rules. The spectral parameter does not change in time. And the second rule is that the wave function here, the derivative, time derivative minus A times psi acting. So now this becomes still a solution to, in fact, that there's a typo here. So I should have psi, and then I should have this here. So this should be a solution to this equation. Namely, if you replace psi on both sides by this, then the linear differential equation should be satisfied. So again, my apology that so this one and this one should be interchanged. And then the final rule is that, well, this is a linear differential operator, but it should be the 0 multiplication operator. So when you impose that condition, then you will derive the nonlinear partial differential equation. So if you apply this, the lax procedure, then you get for the unknowns q of xt and p of xt, you get this 5th order nonlinear system. So as you can see, we have the time derivative, the 5th x derivatives, and then all the remaining terms are nonlinear. And so the lax pair in this case is well known. And if you look at this, there are 2 potentials, q and p, and d is certainly the d by dx, the x derivative operator. And the time evolution for this will be given by this linear differential operator. And now, if you look at the linear part, well, it is nothing but this. So the general 3rd order linear ODE, and I mean, without loss of generality, as you know, we can choose the 2nd derivative equal to 0. So there are 2 potentials in this case, and so there is the spectral parameter, and this is on the full line, then x is in R. And now we can discuss the relevant wave functions. And if you like, we can analyze the problem at t equals 0 or analyze it at some fixed t. So we can obtain the scattering coefficients, or we can obtain the time evolved scattering coefficients. And then we can look at the bound state information and see how the bound states are evolved. Now, there are two special cases of this nonlinear system. In fact, hardly anyone studies this full nonlinear system. So, because physically, only two cases, well, only a few cases are relevant as far as describing the physical phenomena. So one of them is known as the Savada-Kotera equation, and that corresponds to the case where one of the potentials P is 0 and Q is real value. And then the nonlinear system of two equations reduces to a single equation. And I'm going to suppress the T dependence, but we have this equation. And the second case is when P is the X derivative, and again, Q is real value, but even in that case, you have the same nonlinear PDE. And now, from my point of view, you really don't need to make any distinction between these two, because you can just study the problem. So this problem with Q and P in general. But in the field of integral systems, they make a distinction. Now, another integrable system related to the third order linear ODE is, well, it's the bad Boussinesq. Well, I mean, even the good Boussinesq is related to the third order ODE. So, but I'm not including in my talk the good Boussinesq. Well, so as you know, the bad and good adjectives were introduced by McKean. So they call it the bad Boussinesq because so this system describes the surface water wave propagation along canals, and for bad Boussinesq system, there is some solutions that blow up in finite time. So that's why this is called bad Boussinesq. And so the linear operator here in this case is the third order operator, but it is, in this particular case, it is self-adjoint. And so in that sense, more can be said about this case, bad Boussinesq system, than you can say about the Savada-Kotera or Karl-Kupperschmidt case. And here's the, so you can eliminate, so even though the system is first order in time, but you can eliminate P, and you can just get one single equation in Q, and Q is assumed to be real, and here's your bad Boussinesq equation. Well, these coefficients are really not important because, as you know, you can do a scaling. So you can multiply, T by a positive constant times T. You can multiply Q by a positive constant times, you can multiply X by a constant times X. You can multiply Q by a constant, and then you can scale these. And so you have the bad Boussinesq when you have a minus sign, and when you have a plus sign here, you have the good Boussinesq equation. And this says, well, if you want to do the inverse scattering problem, or if you want to do the inverse spectral, inverse scattering transform, just analyze this. So the spectral parameter, and in fact, you can analyze this basically by having Q here and by having P here. And then you can just confine yourself to the special case. Again, you can define the scattering coefficients, time-evolved scattering coefficients. Well, you can study the bound states or time-evolved bound states. And then in the reflectionless case, you can get the explicit closed form solutions, those so-called Soliton solutions. And so here's, so basically this also indicates the need to study the third order linear differential equation on the full line. And well, it turns out that there are two fundamental solutions, and they are known as the Yost solutions. And in fact, you can guess that all the terminology are imported from the second order case. And it's possible to construct two additional solutions to this equation, because in general, this is non-self-adjoint, and the construction of these two other solutions will involve using the solutions from the adjoint equation. But if you have a self-adjoint equation, then you don't need to use the adjoint equation. Well, in any case, you can define the scattering coefficients. Well, actually, it depends on how you set up the scattering problem. So, but, well, being partly coming from physics, I feel that it is nice to work with the scattering coefficients. Whereas in the mathematical formulation, you're going to get L of K times T L of K inverse, or M times T L of K inverse, or R times T R of K inverse. So those are going to be the coefficients. And most mathematicians or people in the field of integrable systems do not separate do not separate the scattering coefficients, or when they say scattering coefficients, they may actually be referring to, for example, L times TL inverse. So the bound states, well, so how do you analyze the bound states for this? Well, so you can define the bound, you can describe the bound states either by using the bound state norming constants, or first introduce the so-called dependency constants. And so again, in my opinion, it's nice to first talk about a dependency constant, and then go to the norming constants, bound state normalization constants. But the advantage of this is that, as you know, for some non-self-adjoint problems, bound states may occur anywhere and may have multiplicities. So if you use dependency constants, then you can handle the multiple bound states and bound states with multiplicities. And then in case you would like to apply this to integrable nonlinear systems, well, then you need to know the time evolution of everything, but that time evolution is easily obtained by using this rule that I mentioned. So this quantity should remain a solution to this, and by using that principle, you can get the time evolution of all the solutions, time evolution of the scattering coefficients, time evolution of norming constants, time evolution of the dependency constants, etc. Okay, and then in the reflectionless case, well, you can get the explicit closed form solutions. And so here, so I'm going to call these the two potentials, and for simplicity, you can just assume that these belong to the Schwartz class, so that they vanish very fast as x goes to plus infinity and minus infinity. And so here's the unperturbed problem when the potentials are 0, and if you look at the unperturbed problem, so you can solve this explicitly, and the three fundamental solutions will be e to the kx, e to the z kx, e to the z squared kx, where z is the cube root of unity. So as a result, these will become complex solutions. And since p and q become 0 when x goes to plus and minus infinity, that means any solution to this, at least any proper scattering solution, should behave like this asymptotically. And so that means you have 6 coefficients, and this is third order. So you can choose 3 of the coefficients to get a particular solution, and the remaining 3 coefficients in the asymptotic expansion will give you the scattering coefficients. And so you can interpret the scattering scenario. Well, I'm a little embarrassed because I'm talking to the experts in scattering theory. Basically, so you interpret this as the incoming wave from x equals minus infinity, and it is transmitted in the same channel, and this is the transmission coefficient, and then it is reflected into 2 other channels. And then I'm going to call this the primary left reflection coefficient because it is originating from the incoming wave coming from the left. And this is my secondary left reflection coefficient, and this is my transmission coefficient from the left. And then you can also have, I guess, the reverse of this. So you can have the incoming wave from this direction, and then the transmission coefficient from the right. And then you can have here the primary left, primary right reflection coefficient, secondary right reflection coefficient in this channel. Now, when you do this, so it turns out that, in fact, I guess this is well known because if you have a second order equation, you need to divide the complex K-plane into 2 regions by using the real K-axis. So if you have a third order equation, you need to use 2 lines. If you have, I guess, a higher order equation, in fact, this was mentioned in Mikhail Ignatiev's nth order study. So then you use more lines, more full lines to divide the complex K-plane. So here I'm being more specific. So it turns out that you get these particular solutions. F of kx will lie here in omega 1. This is the closure. And h down, so will lie here. That's going to be the k domain of h down. And this is going to be the k domain of another particular solution, g of kx. And I'm going to have a solution that I construct by using the adjoint equation. And then by replacing k by zk and z squared k, I can get, at any point, I can get 3 linearly independent solutions. And as far as the scattering coefficients are concerned, the primary left reflection coefficient will live here. The primary second m of k will live here. R of k will live here. And n of k, the secondary right reflection coefficient, will live here. And the transmission, left transmission coefficient will live here and here. The right transmission coefficient will live here and here. But then you will be able to do a meromorphic extension from the boundary to the interior. So as a result, the domain of T sub L and T sub R will be meromorphically extended to omega 1 and omega 3 respectively. And here's I called the left yoke solution. basically it'll behave like e to the kx when x goes to plus infinity. In other words, I'm choosing this as 1, this as 0, this as 0, then these will determine when x goes to minus infinity, they're going to determine my reflection coefficients and transmission coefficient. So here from your solution asymptotically, when x goes to minus infinity, you get the reflection coefficients, the primary left reflection, primary right reflection, I'm sorry, secondary left reflection, and then T sub L, but as you know, you have the inverse here. But if you multiply both sides by TL of K, then you get the so-called physical solution from the left. And you can do the same thing with G of Kx. So this is going to be the right Yost solution. It behaves like e to the Kx when x goes to minus infinity, and it's going to be a combination of e to the Kx, e to the ZKx, e to the Z squared Kx when x goes to plus infinity. And this is how you introduce the right scattering coefficients. And so here I have the right transmission coefficient, the right primary reflection coefficient, the right secondary reflection coefficient. And now you can formulate the Riemann-Hilbert problem, and this is usually done. So everybody does this. And when you formulate the Riemann-Hilbert problem, you find the relationships among certain solutions on these core half lines. And then you have those solutions have some analytic or meromorphic extensions to these interiors. And then you somehow normalize the solutions at k equals plus infinity. And then you solve your Riemann-Hilbert problem. Now, the only problem here is that we have two lines, two full lines. Whereas in the second order case, you only have one line, and this line, remember in the Schrödinger case, it is the real axis. So if I had two half lines, then I would be able to identify my minus region and my plus region in my formulation of the Riemann-Hilbert problem. And then I would be able to identify my minus function and plus function. And from the jump on this line, I would be able to solve my Riemann-Hilbert problem. In fact, you can see that here, this half line is L3, and I change the sign so that I get this full line, which I'm going to call this L. So if I can do this, then I can apply the technique that I know from the second order case, from the Schrödinger case. Well, it turns out that you can do this by choosing the secondary reflection coefficient equal to 0. In fact, this idea, so we were inspired by the paper by Dave, Tomei, and Trubowitz. So basically they said, look, let's apply the technique of, essentially that technique was so originally by Fadeev, but Dave and Trubowitz, if you recall, published a paper in 1979. So by choosing the secondary reflection coefficients, remember they live here and here, I'm able to establish my plus function, and that will have the domain here, my minus function that will have domain here, and so this quantity is defined in omega 1, so it's right here, and this quantity is defined in here, but then these two will be, those two functions will be meromorphic continuation, namely, you're not going to have a jump here. And similarly, I'm going to define a meromorphic function here, a meromorphic function here, without a jump here, so that basically I can reduce this to this Riemann-Hilbert problem, now formulated on a single line, and then I can use similar techniques applied to the Schrödinger equation. And so you can show that if and only if this one is 0, then these two will be analytic continuation. I'm sorry, meromorphic continuations of each other. And if and only if n, the secondary right reflection coefficient is 0 here, then these two will be continuations of each other, so that I have a single minus function and a single plus function. Then I can just essentially solve my inverse problem. In fact, you can tell another advantage of this is that by using the L2 Fourier transformation here, you can also formulate an integral equation, which I call the Marchenko integral equation, or the Marchenko-like integral equation. And now, by choosing the secondary reflection coefficient equal to 0, so you have your Riemann-Hilbert problem, and this is the jump across L, where L now is this line, this directed line. And this is my plus function, and this is my minus function, and these two will have a jump across L. And that you can evaluate that jump is now given explicitly in terms of the reflection coefficients. Voila! This is very similar to the formulation in the case of the Schrödinger equation, and the only difference is that you don't have this on the real axis, but you have it here. But it doesn't matter. I mean, so now you can solve the Riemann-Hilbert problem given the reflection coefficients. You can solve the Riemann-Hilbert problem, and you can also do this when you have the bound states, because the bound states, so it turns out the bound states will correspond to the poles of the transmission coefficient. But for simplicity, I'm assuming that we don't have any bound states. So if you know the jump, namely, if you know the coefficients in the jump, then you will be able to solve this Riemann-Hilbert problem explicitly and recover phi plus and phi minus. And from phi plus, you can recover all those solutions to your third order equation. So if you know phi plus, because you know the transmission coefficient, you can get F. Or from phi minus, you can get G, or you can get H down or H up. And from so from this solution, recover F of Kx. And for example, by using the large K asymptotics, 1 over K and 1 over K squared asymptotics, you can recover these quantities depending on X only. And from those, it's just a simple matter that you recover your two potentials. So this is the way to solve the third order equation. So the only minor problem is that you set the secondary reflection coefficient equal to 0, but it turns out that this is not a big deal. Now, here's the relevant prior work. I mean, there's a lot of work, but I'm just stating what is relevant to my case. So it was Kaup that started the study of direct and inverse scattering problems for the third order equation. And Kaup, all his life, tried to find a Marchenko-like integral equation, but unfortunately he could not succeed. It is because he was not able to formulate the scattering problem, because in his formulation, he was formulating the scattering problem on all these. In fact, he did not even separate the reflection and transmission coefficients. So he defined a scattering matrix, but then he had to assume that those plus and minus functions had to, in order to construct them, he had to assume that the potentials had to have compact supports. So it was a mess. So, but and all his life, Karp tried to find that Marchenko-like integral equation. I will elaborate on this a little bit more. And in fact, as most of you know, Diaz and Kaufman in 1980s tried to solve, developed a method to solve the nth order equations. So a third order case is a special case, and they formulated the Riemann-Hilbert problem, but because they did not separate the reflection and transmission coefficients the way I guess I did, so it was impossible for them to come up with a Marchenko-like integral equation. And then came this paper. Well, I mean, the purpose of this paper is to solve the bad Boussinesq equation. Now, well, this is a very nice paper, and these are decent mathematicians. In fact, Tomei wrote his thesis on the bad Boussinesq equation, but by using another method. But unfortunately, they made the following assumption. They said, oh, choose, so these two, choosing the secondary reflection coefficients, this is not bad. In fact, they had the justification because by choosing these, you suppress the bad Boussinesq solutions that will blow up in finite time. So this is acceptable. But then they had to make the assumption that the transmission coefficients were identically equal to 0. In other words, no bound states for the third order equation, or for the bad Boussinesq equation, no Soliton solutions. So they formulated the Riemann-Hilbert problem by using their self-adjoint differential operator. So they did this only in the self-adjoint case, and they were able to use the analytic continuations. So if you use these assumptions, in fact, you can see, so all these are set equal to 1, identity 1, and these are analytic. So then these two become analytic functions. So in fact, we were inspired by the paper by Dave Tomei and Trubowitz, but we felt that this was too severe. In fact, even too severe if you want to study the integrable evolution equations, because after all, when you study integrable evolution equations, you get the explicit solutions in the reflectionless case. But if you choose the transmission coefficients equal to 1, then the only solution that you will get will be the trivial solution. So with this assumption, you cannot have any Soliton solutions, whereas all explicit solutions are those Soliton-like solutions. Now, in 1989, Hirota, a Japanese physicist, came up with a solution for the Sawada-Kotera equation. Well, this is known as Hirota's direct method. In fact, he formulated even a Marchenko-like equation for particular solutions to Sawada-Kotera equation, but this had no relation to scattering. So Hirota was basically trying to use the so-called dressing method of Shabbat and Zakharov to derive an integral equation that looked like Marchenko integral equation. Now, the criticism here is when you have a Marchenko-like integral equation, so that Marchenko-like integral equation should accept the scattering data. But Hirota's Marchenko-like integral equation can accept only a particular form which will be, which it turns out that, but most likely Hirota and his followers didn't know about this. So the input to this Marchenko-like integral equation will be one particular way of choosing the bound states, all on the same line on the complex place, and then choosing wisely the particular dependency constants. But that Marchenko-like equation will only be valid for that particular data. It's not going to be valid for any scattering data. And now there came this paper by Parker, and so Parker said, well, is there any way to explain how to derive the Hirota's integral equation maybe in a more understandable way? Because Hirota came up with this integral equation. Again, no relation to scattering. In fact, let me then elaborate on this a little bit. So here's, so let me start the paper by Kaup. So let me show the paper by Kaup. So Control L and make it larger. So this is the paper, Kaup's paper from 1980. And he's using, and as you can see, he says formally solved. So, I mean, so this is a nice paper, but at the same time, as I indicated, he was not able to separate the reflection and transmission coefficients. And then since he used some different notation, but basically, in fact, so while he went through a lot of pain and he defined his scattering matrix, essentially by using, by relating a plus solution and a minus solution, but he did not, I mean, his formulation was not proper. So you can just go over this paper. So it's a very nice paper. So let me try to, and then he tried to define the individual scattering coefficients, but it was a big mess. So, okay, so, well, you can just look at this paper. Okay, so now let's look at Hirota's paper. So let me make it full screen. And so plus. Okay, so in fact he mentions, okay, so let me make it a little small. Okay, so Kaup tried to solve the inverse scattering problem of the class because Kaup used the class in the title of his paper, but as you can see, even Hirota mentions, but was unsuccessful. And Kaup also realizes this. And then what Hirota did was the following. So, well, Hirota knew about he calls it the Gelfand-Levitan equation, but this is actually a Marchenko equation. And unfortunately, this is a misnomer, and people in the integrable evolution equation community make that mistake. So this is essentially the Marchenko integral equation for the Schrödinger equation. And then Hirota used the so-called dressing method of Shabat and Zakharov on the Sabada-Kotera equation, and then came up with his integral equation. So here's Hirota's integral equation. As you can see, So this part looks the same as the Marchenko integral equation, standard Marchenko integral equation, and this part is different. And so he mentions, oh, in place of this kernel, so use this. And so the basic idea is to use the dressing method because Hirota has nothing to do with scattering theory. Okay, now let's look at the calc. So let's go back to calc. Okay, so let me make it full line. Okay, so as I mentioned, all his life, so Calc died recently. All his life, Calc tried to get that Marchenko integral equation for his third order cubic equation. In fact, there's a typo here, and well, it's so interesting that that typo exists both in the archived version and in the published version. So, so in the unsolved problems, although we have a solution for the inverse scattering transform of the cubic eigenvalue problem, there is still no equivalent of the Gelfand-Levitan Marchenko equations, which you should say the Marchenko equations. So what we do have is the solution of the Riemann-Hilbert problem, and so then so basically is after that Marchenko-like integral equation, but as I mentioned, unfortunately, Calc died a few years ago without being able to get. But he referred to Parker. So let's look at Parker. So so here's Parker's paper. So Parker, so basically he refers to, so he gives an introduction. So this is his version of the Sabada-Quatera, and he mentions, in fact, so here Calc says, he says, Calc solved the third order inverse scattering problem, but Hirota says, no, he didn't solve. So, everything is in the eye of the beholder. So, okay, now, so basically, so here's the equation, the Marchenko-like integral equation that Hirota obtained, and now by using the dressing method of Zakharov and Shabbat, Parker tried to derive this equation. Okay, but it's too complicated. Well, it's no wonder, because let's look at so let's listen to Zakharov. Well, unfortunately, as you know, Zakharov died a few years ago. An excellent mathematician, and so he was a co-inventor of the so-called dressing method, and so the dressing method applies very well on some known equations, but when you try to apply the dressing method, so let's listen, let's hear what Zakharov says. So let us do one concluding remark. A mathematician using the dressing method to find a new integrable system could be compared with a fishman. Well, actually, he means a fisherman, but it doesn't matter. Plunging his net into the sea, he does not know what a fish he will pull out. He hopes to catch a goldfish, of course, but too often his catch is something that could not be used for any known to him purpose. He invents more and more sophisticated nets and equipments and plunge all that deeper and deeper. As a result, he pulls on the shore after hard work for more and more strange creatures. He should not despair. Nevertheless, the strange creatures may be interesting enough if you're not too pragmatic. and who knows how deep that. So you could just, I guess this is very enjoyable paragraph, but that the moral of the story is the following. As you know, so Control L. So here, some people are interested in using the scattering theory and inverse scattering theory. But in the integrable systems, a lot of people say, no, don't use scattering theory because it's too complicated, or you cannot do that, or because it's too cumbersome. And that's why Shabbat-Zakharov's addressing method does not involve scattering. So, okay. So finally, I'm going to conclude my talk. Well, once you have the formulation of the Riemann-Hilbert problem, so you could just, in the standard way, you can take out those exponential terms and then evaluate the large K asymptotics so that you can bring your Riemann-Hilbert problem into a form where you can take the L2 Fourier transform. And by using the L2 Fourier transform, you obtain your Marchenko-like integral equation. Now, so I can just say a few things about the bound states. So the bound states, in the reflectionless case, you have two transmission coefficients. In fact, it turns out that the right transmission coefficient becomes the reciprocal of the left transmission coefficient. In fact, this is the scattering data that is used by Hirota. So basically, his integral equation is valid only in this case, but he doesn't use the dependency constants. He doesn't mention the transmission coefficients, but basically what he does interpret it in terms of the scattering and inverse scattering. He uses this specific transmission coefficient. He uses some specific values for the corresponding dependency constants. And then he uses, so he inputs his integral equation and gets the solution. And so this is how you would do the inverse scattering problem in the reflectionless case. So, for example, if this is your transmission coefficient, in fact, here you have simple. So you have these bound state locations, and then this is the complex conjugate. Suppose we have n of them. For each bound state, you introduce a dependency constant, and it turns out that, so this is your left yaw solution, this is your right yaw solution. Since their domains are different, you need to apply the, so at the bound state, K sub j, now they have the same common domain. So then at that value, these become linearly dependent. And then here's the time evolution of the dependency constant. Basically, you use this bound state information, and in the particular case without reflection, so you solve this Riemann-Hilbert problem, and then you can apply the restrictions to get the Sabada-Quatera, or so you can just get the Cobb-Cooper-Schmidt, or you can use a different time evolution, and then you can get the bad Boussinesq and the good Boussinesq. Ricardo, how much time do I have? So in fact, I can check it here. In fact, I'm much over. So perhaps I was going to do the mathematical demonstration, but I will not. So here's my list of references. Well, I thank you very much for your attention. Ricardo, do I have
Yes,
more time?
you have some 6 more minutes.
Okay, so I'm sorry because I thought that I started at the hour, so I started at, so if you allow me, I will be happy to show you a few mathematical files.
Yes, you have still some time.
Oh, okay, so okay, so let me just go to so here's the one Soliton solution in the Savada-Quatera case. So as I mentioned, so I will explain what the data is, and I'm going to make this full time. And so this is that cube root of unity, Z. And I choose the location of my bound state at k equals k1. And I'm going to choose eta 1 as a positive parameter, so positive constant. And then, so this is the complex conjugate. Now, as I mentioned, for each particular case, I'm going to be choosing my dependency constant in a particular way. Now, what happens if I don't choose my dependency constant in a particular way? Well, this is the same as if you choose your norming constant as positive, then you're going to get a sensible, real solution to your Schrödinger equation, real valued potential. What happens if you choose your norming constant as negative? Well, you're going to get a real solution, but that solution will blow up. It will be will not be satisfied, will not be blowing to a particular class. And what happens if you choose your dependency constant as a complex constant? Well, you're still going to get a solution. You're still going to get a potential, but that solution, that potential, when you solve your inverse problem, will be a complex valued potential. So remember, in the Savada-Quatera case, they insist that I must have the potential real. So that means I need to choose my complex value dependency constant R1 plus I times S1 in this particular way. And the transmission coefficient is K plus K1 star divided by K minus K1 star. So this is basically the Kurota's one Soliton solution. And here's my modified dependency constant, and I'm choosing it in this particular way, but still containing one parameter, one real parameter. And then, so I will then solve, so let me just evaluate the entire notebook. And, okay, so because I'm using an animation, so I need to do this again, because mathematics gives me a warning, evaluate the notebook. So the evaluation is fairly quick. And then, in fact, it evaluated everything. So now here's the potential QXT. And as you can see, I have two parameters, R1 related to the dependency constant and eta 1 related to the location of the bound state. And as you can see here, you can see that I should choose R1 to be negative. Otherwise, I'm going to get a singular solution, but the solution will still be valid. And so as you can see, for every input eta 1 R1, I'm going to get a potential, but if I want to avoid, and so I should choose R1 to be negative. So in fact, I can verify that in this case, P is 0. I have the Savada-Quatera, and then I can verify that the Savada-Quatera equation is satisfied. This is the nonlinear equation. And here I have the Yost solution to my linear equation, the other Yost solution, and you can see those are also satisfied. And then I can just, for example, assign some particular values. So I choose, say, eta 1 to be 1, R1 to be -2, and this is the initial potential. Here, the Soliton speed is 9 times eta 1 to the 4th. So we can even do the animation. So here, this is not interesting because you only have one soliton. In fact, because this is a non-self-adjoint problem, so if you choose R1 to be positive, so then you get a singularity in the denominator, and as you can see, so you'll get a singularity. I mean, you can do the soliton solutions, but the solitons will have a singularity as well. So it's interesting that here the restriction is you should choose R1 to be negative. Okay, now let me quit this. Okay, so I'll say don't save, quit this. And now let me just do essentially the one soliton, but in the Savada-Quatera case. So I'll remind what the Savada-Quatera case does. So in the Savada-Quatera, I'm sorry, this is the Savada-Quatera. So I want to do the Kalb-Kupperschmidt. Okay, here's Kalb-Kupperschmidt. So in the Kalb-Kupperschmidt case, P is not 0, but is equal to Q sub X. But the same procedure applies. Now, one interesting thing here. In the Savada-Quatera, you need to choose R1 negative. It turns out that in this case, you need to choose R1 positive. But otherwise, exactly the same transmission coefficient. So let's run the entire notebook. And again, because I'm running an animation, it say, so let me run it again. So it's exactly the same data. I have one soliton, so location of the soliton and the dependency constant. Or equivalently, you can say the bound state energy and the bound state norming constant. And here's, so practically the one soliton case, this is the initial profile, and then you can do the animation. In fact, here, as you can see, R1 is chosen to be positive. In the Savada-Quatera, R1 needs to be chosen as negative. Okay, now let me just quit from this and then present to you one two-soliton example. So that's going to be the Savada-Quatera. This is the two-soliton example. And because of please stop me in case I went over. So this
Well, maybe you show the example because you are really over time.
okay,
Show,
so let me just show this and stop. So this time I have two solitons, K1 and K2, but they are aligned. I have two dependency constants expressed in R1 and R2. So then, in fact, let me run this quickly and then evaluate the notebook. Okay, and then, so this time Q becomes more complicated because I have the two soliton case. And so let me show you, here's the expression. Okay, so here's the expression. So as you can see, it takes several lines and I have four parameters, R1, R2, eta 1, eta 2. And as you can see, so here, this is the Savada-Quatera. This is the Savada-Quatera two soliton. So P is 0, and so I have everything. So I have the Yost solutions, and so the Yost solutions. So the third order equation is satisfied, and then in a particular case, I have the potential. So then I have the two solitons, and then you can just use so this is like the KDB. So in fact, so the solitons are outside, and so in fact I can slow it So you can see how the two solitons interact with each other, and the tall soliton comes and overtakes the smaller soliton. Well, I'm going to stop here. Well, I thank you very much for your attention, and I'm sorry that I went a little over.
That's okay. Well, thank you, Tuncay, for this very nice, beautiful talk. Are there any questions? Well, otherwise, I have a short question. Well, you got these very interesting results, assuming that M and N are 0. Is it possible to consider cases where M and N are not 0?
Yes, I mean, you can solve the, so let me just, okay, so let's escape, oh, well, okay, don't save, okay. Control L, so, well, you can do that. The only problem is that, then here M will live, here N will live, and your inverse scattering problem will be knowing 4 reflection coefficients, trying to construct the 2 potentials. And in case you have, in the real case, the parameter count, so your problem will be overdetermined. You have 2 real potentials, P and Q, but then you have 4 reflection coefficients. So your problem will be overdetermined, but you can still study that overdetermined problem. And but you will not be able to come up with a Fourier transform on a single line. But you can do the solution on as a Riemann-Hilbert problem on the full line. But as I mentioned, in the integrable community, nonlinear integrable community, it doesn't matter because those 2 secondary reflection coefficients for the bad Boussinesq pause because they blow up in finite time in their time evolution. So you discard them anyway. But in general, if you do the inverse scattering transform, then you will come up with more solutions to even integrable evolution equations containing different types of singularities.
Okay, well, thank you. Is there any other question? Well, otherwise, we thank the speaker.
Well,
okay, and then if there are no further comments, or then I will close the session and we meet tomorrow at 9, always Mexico City time. So, okay, so then bye-bye.